one more observation you can draw from this graph Cm versus alpha. This is alpha and this is Cm. Okay, this is Cm alpha, right? Negative, right? Now let's say you are here at some point. Okay, you are flying at some particular angle of attack. See, I am flying. Okay, now you put the elevator, some disturbance come, for example, not the elevator control, we will not talk about the control. Some disturbance comes and it is the angle of attack has been increased. So I am moving my line this side, moving my point this side, because my angle of attack increases, right? So at this point your Cm was this, and at this point what is the Cm? Cm is decreases, right? Negative direction. That means it is at this angle of attack Cm was this, right? And now when you increase the angle of attack, it is start decreasing, negative. That how you can see. You have a feel for, right? How from the graph you are getting the feel for how the aircraft is countering, right? At one angle of attack I am flying. When disturbance comes, the angle of attack increases, and now aircraft shows the tendency to push nose down, right? And Cm is going down, right here, right? So Cm down is what? Negative, right? And here it is negative. So that kind of feel you have. Okay, but as of now we are not getting this. We are not getting this. So somehow I want this, but in a present case we have done the wing alone only, which is unstable case. So now I will put some tail. Okay, now this is CG, let's say. Okay, or we will draw the wing and tail combined. Okay, this is wing I am drawing and this is tail I am drawing. Okay, this is let's say LT. Okay, and I am using symmetrical airfoil, right? I am using symmetrical airfoil, so I will not show moment about aerodynamic center. Okay, LT. Let's say CG is somewhere here, for example, or CG you should show at the wing, because everything should make sense. Okay, this is CG. Okay, now you may draw the angle of attack, lift for the wing, C by 4. Already we have done, no? But now I am interested in a tail part. Okay, now, so what is the first step? Ultimately we are dealing with moment only, force into distance, right? So we'll put moment produced by tail is LT, this distance is LT, and into lift of the tail. Simple, no doubt, right? Why negative? Because again it is countering, right? Nose down. Okay, LT. Okay, now you can divide this by half rho v square. Now here I will write mt equal to minus LT. You people have noted down, right? Mt equal to divided by half rho v square SC bar. Okay, same thing, half rho v square SC bar. You can write this half rho v square SC bar Cm tail, half rho v square SC bar. This you can write LT. This you can write half rho VT square ST square and CLT. Why TT I am writing? Because you assume that there will be not fresh flow the tail will experience. Okay, so that is why I am putting VT everywhere. Okay, so half rho V square S C bar. Okay, now this will cancel this. In right hand side you will have a CM, left hand side you will have a CMT, and in right hand side what will we be having? I will call half rho VT square divided by half rho V square as a eta, tail efficiency factor. Okay, dynamic pressure at the tail dynamic divided by dynamic pressure on the wing. It will be the eta. Okay. So I will write Cm tail LT and eta, this ratio, this two ratio, this ratio. Okay. Okay. Eta ST S C bar. Perfect, right? Now, what is ST LT? I will divided by SC bar. I will call it as a horizontal tail volume ratio. Okay. So eta VH CL tail. Okay. Now, you may further write CT as a CL alpha of the tail into alpha of the tail. Why I have not write CL naught of the tail? Because it is a symmetrical airfoil. So I will directly write CL alpha of the tail into alpha of the tail, because CL naught of the tail is 0 because it is cambered. Okay. Now I told at the beginning of the class, right, you will use the angle expression later, right? So you can see, go back to this slide, first slide, you use alpha t, alpha w minus I w minus epsilon plus I t. Okay. You put this alpha t expression here, CL alpha of the tail, this is alpha w minus I w minus epsilon naught plus I t. Okay. This is Cm alpha of a tail. Now you defined epsilon, here epsilon naught. What is epsilon naught? Is downwash angle. So you may further write, it is a simple to model using Taylor series, right? Taylor series is nothing but what? First order, right? First order Taylor series you can expand dou epsilon by dou alpha into alpha. Simple. You can say CL equal to CL naught plus CL alpha. Alpha also comes from the Taylor series. Cm equal to Cm naught plus Cm alpha, alpha also comes from Taylor series. If you take just first order, okay, you neglect the higher order term. Okay. And why I am doing this? Because we have to separate the part which is directly dependent upon angle of attack, directly associated with the angle of attack. Okay. And another term which is not dependent upon the angle of attack. For example, let's say if you select the airfoil, CL naught will not depend upon the angle of attack, right? Only, for example, like a, oh sorry, I would like to correct myself. We want to why we are writing CL equal to CL naught plus CL alpha into alpha? Because we want to separate two parts. One is this part, intercept part, and another one is a slope part. Okay. That is why we are doing this. Okay. Now, please be with me. Eta VH. What was this CL alpha of the tail? Please correct me. And this is alpha W minus IW minus epsilon naught minus dou epsilon by dou alpha into alpha of the wing plus IT. Please correct me. Correct, right? So now you can further rewrite Cm naught of a tail plus Cm alpha of a tail into alpha of a tail, or alpha of the wing. We have to consider the reference angle. Okay. Minus eta VH CL alpha of a tail, and this you can write minus IW minus epsilon naught minus IT and plus 1 minus dou epsilon naught by dou alpha into alpha. Okay. Okay. Perfect. Now you can compare, you can find out what is Cm naught. Cm naught is minus eta. We'll make positive here because we will take minus sign outside. So IW plus epsilon naught minus IT. Okay. And then Cm alpha of a tail minus eta VH CL alpha of the tail 1 minus dou epsilon naught by dou alpha. So these two expression we have found out for a tail. Okay. Now closely observe this expression. What we want to get, Cm alpha negative, right? And now see the tail is contributing minus this quantity positive, this positive, this positive, this positive, this is negative. Okay. This positive, and for let's say, and for Cm naught we want positive Cm naught, right, in order to trim the aircraft at a positive angle of attack. So this positive, this positive, this positive, this also positive, this also positive, you can give the tail setting angle negative to make Cm naught positive. That is why you might have heard that key in many aircraft it is this tail negative tail setting is given. Why? The reason is this, to make the positive trim, to trim the aircraft at a positive angle of attack. Okay. Now, but this is what is a complete Cm naught? This is Cm naught of a wing plus Cm naught of a tail. And since we roughly assume that fuselage body is almost symmetrical, right, top and bottom, right, Cm naught you can neglect for that, but Cm alpha you cannot neglect for the same, for fuselage. Okay. So what is the value? Cl naught of the wing xcg by c minus xac by c of a wing. Please correct me. Okay. It is, we have to be very careful here. Okay. Plus eta VH CL alpha of a tail IW plus epsilon naught minus IT. Correct. Please verify each term. Okay. And what is Cm alpha? Again Cm alpha of the wing plus Cm alpha of the tail. As of now I am not including the fuselage part. Okay. So what is this? Cl alpha of the wing xag by c minus, although the fuselage contribution will be less compared to the wing and tail, plus eta VH minus eta VH CL alpha of the tail 1 minus dou epsilon by dou alpha. In weight estimation part which we have covered, right, have you seen? VH we have assumed, right, eta we assume, right. Perfect. MAC double. ठीक है, perfect. Okay. Now you calculate this. Now already I told that when you put the tail, what you are doing, you are taking aerodynamic center behind the CG. Okay. So where now after placing the tail, what is the resultant aerodynamic, where it is located, we have to find out. Okay. So when you consider only wing, it is called aerodynamic center, and when you consider the complete aircraft, it is neutral point. Okay. So what will be the neutral point? आपने उसको एरोडायनामिक सेंटर को कहाँ लेके गए, वो भी तो डिस्टेंस पता होनी चाहिए ना. लेके तो गए टेल लगा करके, पर कहाँ लेके गए, Now we will find the expression of a neutral point. Okay. So neutral point. Neutral point. Okay. So neutral point is a aerodynamic center of an entire aircraft. At neutral point, you will have what? You will have Cm alpha equal to 0, because Cg and neutral point, if it is coincide, what will happen? Your Cm alpha will be 0. We will see, no problem. Cm alpha, it is what? Cl alpha xCg by C, or other way you can define, neutral point is that Cg location where the aircraft become neutrally stable. Cm alpha is 0. Okay. XAC of the wing, okay, minus eta. What is VH? VH is ST. LT you may write XAC of the tail minus XCG by C bar eta VH into CL alpha of the tail and 1 minus dou epsilon by dou L. See, LT is nothing but the difference between tail aerodynamic center and CG. See this. This is the aerodynamic center of wing, right? And this is the aerodynamic center of tail. So if you are considering the wing leading edge, this is XAT and this is XCG. So XAT minus XCG is only LT. Okay. So if XCG is XNP, matlab CG is that, I told you the definition, right? See, neutral point is that point, that CG location where planes become neutrally stable. Cm alpha 0. Okay. Neutrally stable means not diverging, not converging. Okay? So you may write CL alpha of the wing XNP by C bar minus XAC of the wing by C bar. Okay. Or from the new line we will start. New line we will start to avoid the possible confusion. CL alpha of the wing XNP C bar XAC of the wing C bar. Okay. And minus eta VH is XAT minus XCG SC bar 1 minus dou epsilon by dou alpha, and CL alpha tail also we have to multiply. Okay. And X in XCG you will put XNP. Okay. So can you, what you can write XNP? XNP, take one side, you will write minus minus plus. Okay. So you can write CL alpha of the wing XAC of the wing plus eta eta 1 minus eta CL alpha of the tail 1 minus dou epsilon by dou alpha into XAC of the tail divided by CL alpha of the wing plus eta CL alpha of the tail okay. Are you aware of CG M1 X1 plus M2 X2 divided by M1 plus M2 where M1 M2 is a mass? Observe this, it is very beautiful expression. This part this part this part and M1 X1 M2 X2 divided by M1 plus M2. What is M1? Mass, right? If you multiply by the G, it was weight, right? And it is CL alpha. If you multiply by, if you dimensionalize this, you can get the lift force, right? Equal, similar to this, right? So force into distance plus force into distance divided by force plus force. And one force coming from wing, another force from coming tail. Okay. तो जैसे वेट की बैलेंसिंग होती है वैसे लिफ्ट फोर्स की भी एक बैलेंसिंग है जहां पर चीजें बैलेंस हो रही है. दैट पॉइंट इज नोन एज ए न्यूट्रल पॉइंट. ये दूसरी ऐसी डेफिनेशन भी बना सकते हो, राइट? And this epsilon naught and dou epsilon alpha you can also in this where it is I have written, you can further rewrite. Okay, this here you can write dou epsilon naught by dou alpha, it is 2 CL alpha of the wing into pi into aspect ratio, E into aspect ratio, and epsilon naught is CL naught of a wing pi into E into aspect ratio. Okay, this is the expression dou epsilon dou alpha and epsilon you can find out. Okay, if your aspect ratio is very large, then dou epsilon dou alpha will be very low. Okay, and epsilon also will be low. So for a glider kind of aircraft, this effect is minimal. No downwash, there will be less downwash, right? क्या होता है, स्पैन ज्यादा है ना, I'll explain to you, right? And for a fighter craft is dominant one. Okay, and you also kindly verify whether E is there or not. Okay. Now initially this was my lift and this was the tail lift after that, and CG was somewhere here. Okay, now due to this tail I move this aerodynamic center somewhere here, and this point as a neutral point we have located. Okay, now distance between neutral point and HCG with respect to the chord is known as a static margin. मतलब how the CG travels. For example, like if you have a static margin 15%, 20%, 30%, which case the aircraft is more stable? Which case? Static margin is 10%, 20%, 30%. In which case the aircraft is more stable? See this diagram. 30%, right? So now you have a feel for the static margin also, right?